Hello, stat students. In 3.1b, we are going to talk about correlation. Correlation is known as the R value. The correlation R measures the direction and strength of the linear relationship between two quantitative variables. It measures how close the data comes to forming a straight line. Here are some facts about correlation, and this always seems to be something you're asked on multiple choice questions, either on the AP exam or one of my exams. The correlation R is always between -1 and +1, including those as well. A correlation of 0 means there is no pattern whatsoever. The closer the number gets to 1, the closer the dots come to forming a straight line with positive slope, because that's +1. And that, remember, means positive association. The closer the number gets to -1, the closer the dots come to forming a straight line with a negative slope, known as a negative association. Correlation is a numerical way to measure the linear strength of a scatter plot. And so if you look at below, you have basically a number line from -1 to 1, and it indicates where the weak, moderate, and strong relationships are for both the positive and negative direction. So if you look at the weak, anything with a correlation from -0.5 to +0.5 is considered weak. And from zero point 0.5 to zero point 0.8, either positive or negative, is considered moderate. And then zero point 0.8 to 1 is considered strong. So without actually knowing what the R value is, we guessed last time whether something was strong, moderate, or weak. Here, we still are going to guess in the first few examples because we are going to determine what we think R is based on this number line. So let me just write down this is the negative association side, and this is the positive association side. Oops. Okay, so let's take a look at the first one. Okay, sketch, pretty wide, wider. So honestly, you can't really tell. If you can't tell whether it's positive or negative, I would go for 0 here. So R equals 0 because you can't really tell the direction. I'm going to call that weak. Again, you can have cases for this. There's a little activity on your modules where you can guess the correlation. I want you to try that out after class, after notes are over today. So for the next one, okay, this one you can, based on this point right here, you can tell that it's more of a negative, but not a really good negative. So I'm going to call this pretty weak, but not quite like negative 0.1. I would say something like, now, would you be wrong? No. As long as you wrote that it was weak and gave a valid reason, you would be okay. Okay, the next one, dots are pretty good. I mean, that would be like average, I think. So I would consider that 0.5. If you ended up with a textbook, these diagrams are on page 151 of your book. Okay, here, negative, that we know, and pretty moderate. So you can guess anywhere from negative point 0.6 to negative zero point 0.8 or so. So negative 0.7 is what I'm going to say. It's moderate. So here's the one I want to, I think it's called guess my correlation. But I went ahead and put the little applet on there that you guys can play. Okay, and the next one, even closer, positive. Okay, so I'm going to call this closer to like 0.9. So strong. Okay, and then by the way, for this one, before I go on further, the 0.5, it can be either, I mean, you can call it weak if you're going to put the numbers inclusive from the bound for the boundary, or you can call it moderate. It's just right there in the middle. Okay, this one's really good. I'm going to call this like negative 0.97 or 99. It's very strong negative association. Okay. Here's a sample problem. A recent study discovered that the correlation between the age at which an infant first speaks and the child's score on an IQ test upon entering elementary school is negative 0.68. So remember, that's if you look at your number line up above, that indicates moderately strong negative correlation. So let's write that down here. Moderately strong negative correlation. A scatter plot of the data show a linear form. Okay. Which of the following statements about this finding is correct? And always remember that if you haven't studied it or haven't talked about it, you can cross those out automatically. So let's just look at the choices. A. Infants who speak at very early ages will have higher IQ scores by the beginning of elementary school than those who speak later. Now, this is kind of jumping to a cause and effect, and that's in chapter 4. And that only, a cause and effect can only be explained if there's an experiment. So, oops, we're running out of room here. It's not that one. Choice B, 68% of the variation in IQ test scores is explained by the least squares regression. Okay, so you haven't even talked about least squares regression. We will in this chapter. So cross that out. So that leaves us with C or D. C, encouraging infants to speak before they are ready can have a detrimental effect later in life, as evidenced by their lower IQ scores. Okay, so for this one, okay, we know that as speaking age increases, or I'm sorry, this one says as speaking age increases, IQ decreases. Okay, and then the last one. There is a moderately strong negative linear association between age at first spoken word and later IQ test score for the individuals in this study. So this is the best description of this particular scenario. Okay. Now, how do you calculate correlation? And when we know that it's a number between negative 1 and 1 inclusive, there is a formula, and this formula is on your formula sheet. And it is this formula that's given right here, an easier way to remember. Well, maybe not so easy, but makes it more easier to understand. It's 1 over n minus 1 times the sum of the product of x, so that's an individual value, minus the mean over the standard deviation. Hope you remember what that is. That is the z-score. So z-score of your x's times the z-score of your response variable. So y minus, and you would do this for each of them, um, y bar over the standard deviation of y. And that multiplied together and then divided by n minus 1 will give you the correlation. So um, you multiply the z-scores for each observation in the data set, and then you add them all together, and then you divide by n minus 1. We are going to do this problem at the very end so I can show you in another video how to enter all the information. But we're going to skip to the end and talk about facts about correlation, and we don't need that specific example to do this. So the facts about correlation are on page 156 in your book. And this is also multiple choice type questions. So both values must be quantitative. Correlation does not work for categorical data. Another fact, if you switch your response variable and explanatory variables, the correlation doesn't change. And the reason why is you're multiplying their z-scores, and the order doesn't matter when you're multiplying, so it doesn't change. If you change, not your, okay, if you change the units of any variable, the correlation does not change. Correlation has no unit of measure. It is just a value. Okay. A correlation close to 1 does not guarantee that it is not curved. So you must check your graph. So just because it has a correlation of 1 does not mean that it's linear. It could still be curved. It is sensitive to outliers since the mean and standard deviation, which we learned already in a previous chapter, are affected by outliers. And mean and standard deviation are used to calculate correlation, as we saw up above. We have the mean here. We have the standard deviation. So correlations are sensitive to outliers. And correlation only measures how close the data fits to a line, not how it fits to a curve. And I want to add one last one in here. Correlation does not imply causation. So the cause and effect we'll talk about in later chapter. All right. And that is it for the written part of our notes. I want to do the graphing calculator portion in a separate video. That is it for 3.1b. Have a great day.